Here we see a circuit with multiple loops, where the currents don't just flow straightforwardly. They split and then come back together, so using Ohm's law alone won't give us the full picture of how the currents behave. Instead, we need to consider the entire structure and apply conservation laws that take into account how voltage and current distribute in this interconnected system. Kirchhoff's first law is based on the conservation of charge, which means that charge cannot be created or destroyed within a circuit. This law tells us that the amount of electric current flowing into a junction has to be equal to the amount of current flowing out. In the diagram, currents I1 and I2 are flowing into the junction, and I3 is flowing out. So when we add I1 and I2 together, that sum must be equal to I3. This ensures that the total current is balanced at any connection point in the circuit.
Kirchhoff's second law is based on the conservation of energy. It tells us that in any closed loop, the total energy supplied by the power source, or the electromotive force, is exactly balanced by the total energy used up by the components in the circuit, like resistors. This means the sum of all the voltage rises equals the sum of all the voltage drops around the loop. In other words, the energy you put into the system is completely accounted for by the energy each part consumes, which is why the equation shows the sum of EMF equals the sum of current times resistance. This principle helps us analyze circuits and understand how energy moves through them.
We start with Ohm's law, which focuses on resistance and relates the voltage, current, and resistance in a single component through the equation V equals IR.
Next is Kirchhoff's first law, based on the conservation of charge. By applying these laws, you can systematically approach circuit analysis, focusing on single components, junctions, or loops as needed.
Kirchhoff's second law focuses on the conservation of energy and states that, around any closed loop, the sum of the electromotive forces equals the sum of the voltage drops. This law is essential when working with closed loops in circuits. Together, these principles and equations form the foundation of circuit analysis. The first step is to clearly define the geometry of the circuit. Start by identifying all the nodes, which are the points where components connect. Then, determine the closed loops within the circuit. These loops are essential for applying circuit analysis methods like Kirchhoff's laws. Finally, assign assumed directions for the currents in each branch, and be consistent with these directions throughout your calculations, even if you later find the currents flow opposite to your assumptions.
According to the principle of conservation of charge, the total current entering the node must equal the current leaving it, so we write the equation I1 plus I2 equals I3.
Then, for the loop that includes the voltage source and resistors, we use Kirchhoff's voltage law, which states the total voltage around a closed loop is 0. This gives us the equation where the voltage from the source equals the sum of the voltage drops across resistors R1 and R3, expressed as epsilon 1 equals I1 times R1 plus I3 times R3.
Similarly, in the second loop, the voltage from the second power source equals the sum of the voltage drops across resistors R2 and R3 with currents I2 and I3.
Slide 13. Slide 13. Now, let's focus on solving the system of equations we established. The first equation relates the currents, showing that the current I3 is the sum of I1 and I2. Using that, we substitute I3 in the next two equations, which represent the voltage drops in the circuits. These voltage equations include the resistances and the currents, and by substituting I3 as I1 plus I2, we now have expressions that connect all variables. One important point to remember is about the negative sign in your results. If you find any current calculated to be negative, it simply means that the actual direction of current flow is opposite to the direction you initially assumed. This is a common and acceptable outcome, so it's a helpful reminder not to worry when you encounter a negative value. It just clarifies the true direction of the current.
The outer loop check here applies Kirchhoff's voltage law to the large outer perimeter of the circuit, ignoring the middle branch for simplicity. When we sum the voltage contributions from the two batteries and the voltage drops across the resistors in the outer loop, they add up exactly to 0.
If you found this presentation helpful, I encourage you to visit physicsib.com, where you can access a structured and interactive course designed to deepen your understanding and support your learning journey in physics. It's a great resource to explore concepts more thoroughly and practice with guided exercises. Please consider liking and subscribing to stay updated with more physics resources. For a more structured and interactive learning experience, visit physicsib.com, where you can explore courses designed to support your studies effectively. You can find a link here that takes you to a set of circuit problems along with examples and their solutions. This resource is designed to help reinforce what we've covered by giving you practical exercises to work through and detailed answers to check your understanding. It's a great way to apply the concepts and deepen your grasp of circuit analysis. If you want to explore these problems at your own pace, just follow the link provided.